My name is Jae-Sun from Arizona State University. I'll talk about efficient deep learning hardware designs for image, speech, and biomedical applications. So the success of machine learning and deep learning in recent years has started to substantially change our lives. To name a few, DeepMind's AlphaGo has beaten the best human Go player. Many companies are aggressively pushing self-driving cars, and speech recognition-based systems has been adopted in many of our homes. Starting from the same kind of algorithm plot for image recognition made by Purdue researchers, we can see that there is very intensive requirements on computation and storage to get high accuracy. And you can imagine that if we're trying to port or map this onto some ranges of different embedded hardware, namely self-driving cars, mobile devices, or wearable devices that has severe power and area constraints, it can be quite challenging. So to design intelligent hardware with this power and area constraints, energy efficiency becomes crucial. And to enable this, some of the specific methods that researchers and both our group have been going on is algorithm hardware co-design, efficient data flow, compression, sparsity, and low voltage operations. So in this talk, I will talk about some of our group's recent work on image, speech, and biomedical applications. To start with, I'll start with the deep convolutional neural network designs on FPGA. So CNNs, or convolutional neural networks, has been the de facto for many practical recognition and classification tasks. Besides the fact that the computation and memory requirements are very intensive, as we saw in the previous slide, another challenging aspect is that the state-of-the-art CNN algorithms change very frequently. And on the other hand, let's say if we're trying to map this onto FPGA, because the reconfigurability of FPGA can be utilized best, different FPGA chips and boards have different hardware resources. So the objective here is that we want to do some optimal mapping of an arbitrary CNN to any given kind of FPGA to efficiently implement this moving target of the CNNs. So the input for this automatic RTL compiler, the input will be a CNN model from software frameworks such as Caffe or TensorFlow, and the output will be synthesizable RTL codes. Looking at the deep CNNs, the convolution operations will be constituted of several loops. As we define it, loop 1 constitutes of the element-wise MAC operations within a kernel window, like 3x3, 5x5. Loop 2 are convolutional accumulations across different input feature maps. And if we do loop 1 and 2, we get one output pixel and one output feature map. We have to iterate this across the input feature maps to get different output pixels in one output feature map. And then finally, we have to iterate this across different output feature maps of NOF defined here. So the loop optimization techniques that we employ are kind of three different aspects to minimize the overall latency, partial sum storage, and DRAM access. So first, loop unrolling or parallelization defines which loops will be parallelized with parallel MAC units that will define the overall processing element, or P, structure and architecture. Loop tiling refers to dividing the entire data into blocks that can fit in the on-chip SRAMs. And this relates to the data locality, determining the on-chip buffer size. And finally, the loop interchange represents the order of, okay, which order are we going to compute these four different convolution loops that I defined in the previous slide. In particular, the specific proposals that we are going with for loop unrolling or parallelization, we wanted to unroll loop 3 and 4 that are pertaining for the output pixels and feature maps, while we want to serially compute loop 1 and 2 to minimize the partial sum communication. In terms of loop order, we wanted to compute loop 1 and 2 first to consume these partial sums as soon as possible, and then move on to loop 3 and 4. So let's look at some small example of, let's say we have a 3x3 kernel. This is the input feature map in the red box, and then we wanted to convolve with a 3x3 kernel. So this is representing the red one in the convolution operations going in within one MAC unit, and then the green pixels are the registers loaded from this input feature map, and these are different weights. And you can see this loop 1 operations is serially computed in different clock cycles shown in vertical rows, where different input pixels and weights have to be loaded into different clock cycles. Now, if we shift this convolution window into the next, you can see that the same weights have to be loaded while we use slightly different input pixels here. And this is the same as we move this kernel window another pixel to the right. And you can see that there's actually a lot of data reuse possibility, which can be achieved by using shift registers and shifting data from clock cycle to another clock cycle. And of course, this kind of reuse is possible in the upper row and the lower row as well. Furthermore, if we employ a couple additional registers in each row, we can see that the entire pixel data here can be reused across different rows to make it more efficient. And once we load it from DRAM, we can exhaustively use it. Of course, to make this data flow possible, we have to have certain data loading mechanisms or control that loads data from the on-chip buffers or SRAMs correspondingly. So we designed a convolutional neural network accelerator architecture that exploits this data flow, where in different clock cycles, shown by different arrows, it loads data and shifts data around correspondingly. And as I said, we are parallelizing loop 3 and 4, which are pertaining to the output pixel and output feature maps. Namely, we are parallelizing it for 3 dimensions of x and y dimensions of the output pixels and different output feature map numbers of 16 output feature maps. And then the partial sum in loop 1 and 2 are consumed within each of these red MAC units such that they don't have to communicate over different MACs. The top level accelerated system that builds upon this looks like this. So I only talked about mostly the convolutional network, but in the most recent, like residual deep network by Microsoft, it includes some different computation or network structures that skips a computation from one layer to another layer that require some different element-wise computations or additions, and also some batch normalizations, which are integrated in this FPGA accelerator. Notably, we make this computation modules reconfigurable such that we hand code different modules in highly parameterized Verilog scripts, and they can be reused by different types, different layers of the same type, and varying layer size are handled by the configuration registers. The RTL module libraries that we design are opened and can be extended with new layers or new CNN structures that might come in the future. And we also integrated with some of this Intel Altera DMA engines such that the DRAM access and communication can be handled together in real time. So there has been a couple other prior works that went this route of trying to develop automatic sort of compiler for FPGAs, and we're comparing some of those recent results here that also map some of the state-of-the-art CNN algorithms, namely VGG and residual net. So you can see that comparing similar kind of frequencies and precisions and DSP units, we are getting the highest kind of giga operations per second that can be computed through this FPGA. And overall, we implemented the end-to-end designs of this very large-scale VGG and residual networks. And notably, the end-to-end latency for a single image can be handled with about 30 frames per second, such that we started from the beginning slide that these algorithms have very high computation and memory requirements, but using the sufficient data flow, real-time operations of this image recognition can be executed on these FPGAs. And this is very flexible, as you can see, by just changing some configuration parameters. Different networks can be ported onto the same FPGA. Switching the gears a little bit, let me talk about some of the techniques that were employed for speech deep neural networks. So convolutional neural networks are important, and I focused on the convolution operations in the first section. But it's worth noting that usually CNNs are also ending with a couple fully connected layers. which means that the neurons are in a vector form and weights are in the matrix, such that the memory requirement for the fully connected layers is very large. And if I try to break down, let's say, VGG in terms of how much weight is coming from the others and the convolution and the fully connected, actually you can see that predominantly it's coming from the fully connected layer. Although this trend is diminishing and people are trying to employ less fully connected layers, in speech applications still this type of fully connected DNNs or so-called recurrent neural networks are kind of the state of the art, and those still employ a lot of large like 512 by 512 type of matrix vector multiplications. Obviously, because these weight requirements are very large, many people try to reduce this by either pruning some of the near zero weights or lowering the precision with nonlinear quantization, sharing the weights. But a lot of the works that tries to prune based on a threshold tends to introduce random sparsity, which means that the sparsity is generated in an element by element manner in this overall matrix. What that means is that although you can get a good sparsity and a good compression, now you also have to store, okay, which weights are non-zero now, right? And that incurs some of the index overhead. And if I look at this deep compression paper that achieved a good compression of 30x or so, at the end, the finally weight memory breakdown looks like this, where the blue is the actual weight and the green are the index. And you can see that roughly half of the final weight, compressed weights actually comes from the index. So this brought us to some motivation on, okay, how can we reduce that kind of index overhead from the inefficiency of element by element sparsity? So what we propose here is a blockwise sparsity, or which we call the coarse-grain sparsity, or CGS. So what we do is we kind of divide this fully connected DNN weights or matrix into blocks, let's say 16 by 16, 64 by 64. And then the blocks we want to actually randomly drop with a probability. One thing that differentiates this from a lot of other efforts is that actually we do this random dropping before training and maintain this kind of drop statically throughout the training. If that can happen with high accuracy for the task we want to do, then after the training is done, compressing that onto this kind of compressed matrix with minimal index becomes straightforward. Of course, that has to, we don't want to sacrifice any accuracy, and we implemented this in different ranges of speech recognition applications with different data sets. So this is depicting the 5-layer DNN, a fully connected multi-layer perceptron, or MLP, for a DARPA resource management database, and I'm reporting the word error rate here for speech recognition. And there are a couple design parameters that we are investigating here. One is the block size, how large the block's going to be, which is going to directly affect the index size at the end, and then how much weight drop are we going to apply in each kind of block row. Obviously, we want higher weight drop and higher block size, but we don't want to necessarily sacrifice the WER, or classification accuracy. So here is one of the data points, and then we also try this in a different MLP for timid database, and in the y-axis here, we're reporting the phoneme error rate, and this is the actual matrix that we randomly selected and trained, and at the end, we can get 8x compression with minimal index, like here, while not really sacrificing the PER. Furthermore, we apply this also to a recurrent neural network, which has a lot of like 512 by 512 matrices in this LSTM-based RNN, and then comparing to a baseline RNN and applying the CGS into different RNNs with different hidden layers and different compression rates, you can see that the WER from the baseline, we can achieve the same or similar accuracy. So as I said, this kind of CGS method has to be done throughout the training process. So we cannot really use an existing training method or already trained network and then just try to prune it. So this is the conventional kind of weight update equation where by backpropagation, we calculate the delta W, the change in the weight. There could be some momentum factors and learning rate. So the additional thing that we apply through the training process is this binary connection coefficient, where starting from that kind of block matrix that I showed you in the couple slides before, we create this binary connection matrix where the selected ones have the Cij value of 1 and the unselected ones have the Cij value of 0 for all the elements there. So what that means is that this weight update equation will be only eligible for all the black ones here, and all the white ones will start at 0, never get updated, and end at 0, such that we can directly compress it. So throughout training, only compressed weights are used at CanC. So this actually has, not only for classification, but also has the potential for compressed training hardware acceleration. But for now, we implemented this for the compressed weights at the end, and we implemented the classification hardware for DNNs and RNNs. And you can see we do kind of one layer at a time for this deep neural network design. Being this speech recognition application, the data rate actually is much lower than image or video. And that's why empirically they found out that 16 or 20 kind of MAC units can be optimal in terms of the speed and area. So these include some selector blocks, and the weight storage will be brought in accordingly to these parallel MAC units. And in 40LP simulation, for this 5-layer DNN, we can get real-time performance with kind of single-digit or even less milliwatt numbers. And combining this 8x, for example, 87.5% weight drop with further reduction in precision, we can get 40x or even higher kind of weight compression comparing to software models, and some of the works have been published in these recent conferences. Finally, let me present some quick results on our biomedical application. So in one of the smart ECG processors that we recently developed, we wanted to do, there has been a lot of ECG processor work that try to monitor our cardiac health in a continuous manner, such as abnormal heart rates or abnormal ECG pulse shapes. But we wanted to combine those cardiac monitoring capabilities with actually security or authentication applications. So besides fingerprint or iris, there has been studies showing that everybody's ECG is slightly different, right? And we wanted to exploit that difference such that we can use that as a modality for biometric authentication. And the objective here was to design a low power area smart processor for wearable devices that can do continuous, not only heart monitoring, but also biometric authentication, that we can authenticate ourselves to access our important private health data. So this is a high-level diagram of the proposed smart ECG processor that has pre-processing or filtering signal processing blocks, and these hardware blocks are shared between the cardiac monitoring authentication functions. We employed some simple neural networks to train and classify for the biometric authentication for many different users. So let me focus on the memory compression techniques that we employed for this neural network. Being this a wearable device and has even severe power and area constraints, we don't really have the luxury of employing a very deep or large neural network. So what we applied here is a simple one hidden layer, kind of 2-layer neural network that has input coming from the pre-processing signal processing outputs, one hidden layer, and one of the output layers. So this output layer comes from the actual data that we collaborated with Samsung to collect on different people's ECG from different sessions. So each of these different outputs will signify a different user or coming from a different session. So we trained this in software, and you can see that the total number of weights is about 480K. But one of the things that we realized is that the users that has been used in the training process, and then the users that will actually use the wearable device once it's deployed, are not going to be the same. It's going to be different. And this actually can be the case for a lot of biomedical or authentication applications, so, which is different from conventional image or speech. So we wanted to actually, to that end, these become irrelevant, so we're going to remove the output layer and then use the hidden layers as extracted features, which will allow us to get rid of a lot of weights that are high volume. So after training, The hidden layer represents a feature vector that is unique for each user. And then to do authentication, we go through a registration phase and identification phase for every real time, similar as we do fingerprint on our mobile devices. And we evaluate the cosine similarity on how close these are. And to further reduce the weight from this neural network, so after we got rid of the output layer, we can reduce the precision into a few bits. And this shows kind of the matrix between the input and hidden layer of neural network 1 that has the range of positive and negative weights. And further on, we employ this hardware-efficient lasso regression. So what that does is each column here has 160 weights, and we apply this lasso such that it becomes sparse with some regularization parameter that we can control. But to make it efficient for hardware, we wanted to have the same sparsity, namely 10% for every column. And then at the end, we can compress this 100 by 160 matrix into 100 by 16 matrix by 10x kind of reduction in the matrix size. So we designed this in a 65 nanometer test chip that does both ECG authentication and cardiac monitoring in real time. At 0.55 volts, continuous authentication in real time consumes only 1.06 microwatt. And this yields high accuracy and low voltage operation. So in summary, I went through this image application first, where we designed an automatic FPGA compiler for deep CNNs on FPGA, and we were able to map one of the most recent residual networks end-to-end with efficient data flow and reuse. For speech applications, I talked about some coarse grain compression with minimal index and loss in accuracy. For biomedical, the 65 nanometer ECG processor computes biometric authentication with compressed neural networks at low voltage. So just reminding you that in the first couple slides, I talked about the enablers for this efficient hardware for deep learning could come from algorithm hardware co-design, data flow, compression, and low voltage. What has been kind of scattered and employed in different aspects in this image, speech, and biomedical applications. Overall, the optimal design points now has to be found exploration in both kind of algorithm and hardware. And this work has been collaborated with many faculties at ASU and students, and has been generally sponsored by these sponsor companies or government agencies. Thank you.